Hello again. This is section 3.6, rational functions. So what we're going to look at in this section is what does the graph of a rational function look like? And then what are some of the key features of these rational functions that we need to pay attention to on the graphs of these functions? Okay, so we're going to start here with just the basic rational function 1 over x. We're going to think about what this graph would actually look like. Okay, so I'm actually going to switch over to Desmos here, and we're going to look at this graph in Desmos together and then talk about some of the key features of what we see on this graph. All right, so in Desmos now, I'm going to graph just y equals 1 over x. Okay, so notice here, we've got these two pieces, two curves, one in the first quadrant, one in the third quadrant. And then we have these key features where it's approaching the y-axis, it's approaching the x-axis, but it never actually touches either of those axes. So what we call those are asymptotes. Okay, so we have what we call a vertical asymptote along the y-axis. That would be x equals 0. So we would say that's a vertical asymptote. And then we also have a horizontal asymptote along the x-axis, and we would say that's y equals 0. So again, that's called a horizontal asymptote. I'm going to switch back to the notes in just a minute and show you exactly how to spell each of those. Okay, but that's what we would call those lines that our graph approaches and never touches. Okay, and so all of your rational functions, okay, in most cases, are going to have those features where you have asymptotes. And so what we're going to be looking for in most cases is where are those asymptotes located? Okay, because in a lot of cases, we're going to have transformations. We're going to have a lot more than just 1 over x here. We're going to have polynomials in the numerator, polynomials in the denominator. We have to figure out what's actually going on with these graphs. Okay. So I'll switch back over to the notes now so you can see exactly what I wrote there. And so again, we have a vertical asymptote at x equals 0. That was the vertical line, the y-axis. Okay, that's one of our asymptotes. And then we also have a horizontal asymptote. That's the x-axis, and we call that y equals 0. Okay, now, in terms of domain and range, if we think about the domain here, because we had that vertical asymptote at x equals 0, we know the graph is never going to cross that point. And so we would say that our domain goes from negative infinity to 0, not including 0, so we use a parentheses, and then a union 0 to positive infinity. And then similarly, with the horizontal asymptote at y equals 0, we know our range is never going to go through 0, so we're going to go from negative infinity to 0 on the y, and then 0 to infinity. So wherever you have vertical asymptotes, those are going to be restrictions on your domain. Wherever you have horizontal asymptotes, those are going to be restrictions on your range. All right, now definition of vertical and horizontal asymptotes. Okay, so the line x equals a is a vertical asymptote of a function y equals f of x if y approaches positive or negative infinity as x approaches a from the right or the left. Okay, so it is possible in this case, right, that from one side we have an asymptote and there's nothing on the other side. So you could be approaching from the left, you could be approaching from the right, you could be approaching from both sides, right? Okay, so that would also be considered an asymptote if as you go towards that x value, your graph goes either towards positive infinity or negative infinity. All right, and then we have a horizontal asymptote, y equals b, of that function if y approaches b as x approaches positive or negative infinity. So as I go out to the right or as I go out to the left now towards positive or negative infinity, if my graph is approaching some horizontal line, okay, then we would say that's a horizontal asymptote. And you can see those two examples down at the bottom. Now notice with that second graph, it's okay if the graph actually passes through an asymptote. All we're looking at now is what's happening at the ends. As I go to positive infinity and negative infinity, am I approaching some line and never crossing it out towards positive and negative infinity? Okay, so even if the graph crosses that asymptote somewhere in the middle, that's perfectly fine. We're only interested in what's happening at positive and negative infinity this time. All right, so now we're going to let R be the rational function. And notice here, I've got the polynomial in the numerator. I've got a different polynomial in my denominator now. These are the polynomial forms that we've been looking at throughout this unit. The vertical asymptotes of that rational function are the line x equals a, where a is a zero of the denominator. In other words, if we can find the zeros of our denominator, those zeros now are going to be the vertical asymptotes, because we know the denominator of a rational function can't be equal to zero. So we're setting the denominator equal to zero, we're solving for x, finding those zeros, and that's going to give us the vertical asymptotes. Now, in terms of horizontal asymptotes, we have three criteria, three rules that we're going to look at. If n is less than m, and notice here, n is the degree of the numerator, m is the degree of the denominator. So if the numerator's degree is less than the degree of the denominator, then R has a horizontal asymptote at y equals 0. Okay, so if we look at the numerator, the exponent in the numerator is smaller than the exponent in the denominator, automatically horizontal asymptote y equals 0. If those two exponents are equal to each other, then we're going to take the leading coefficient, a sub n, and we're going to divide it by b sub n, which is the leading coefficient in the denominator. That's how we're going to get the horizontal asymptote if the exponents are equal to each other. Just divide those leading coefficients. And if n is greater than m, the exponent in the numerator is bigger than the exponent in the denominator, then there is no horizontal asymptote at all. So those are the three rules, right? Smaller exponent in the numerator, y equals 0. Exponents are equal, divide the leading coefficients. Exponent in the numerator is bigger than the exponent in the denominator, there's no horizontal asymptote. All right, so let's take a look at this one. So we want to find vertical and horizontal asymptotes of R of x. Now, the first thing we always want to do with these rational functions is go ahead and factor them, see if anything simplifies, and then we're going to actually look for those zeros to find the vertical asymptotes, and we can do our division if we need to find the horizontal asymptotes. I'm going to look at my numerator here, see if there's anything we can do to factor this. So if I try to break this up this time, I know 3x squared could be 3x and x. I know 1 only has factors of 1 and 1. In this case, I need a negative 2x, so I would need a negative 1 here and a positive 1 here, and that would give us what we started with. Now, same thing in the denominator. See if we can factor that. So 2x squared is going to be 2x and x. Then the factors of 2, all we have here are 2 and 1. I'm going to put the 2 here and the 1 here because I know I'm trying to get a 3x in the middle. If I do a plus here and a minus here, that'll give us 4x and minus 1x. That would give us 3x in the middle. Now, the whole reason for factoring first is to see if we have any common factors that might cancel out. In this case, there are no common factors in numerator and denominator, so we can stop right there. Okay, but we know we're going to set the denominator equal to 0 anyway, so by factoring it, we've already kind of done that first step of setting it equal to 0. So now what we can do is just take 2x minus 1 times x plus 2 and set that equal to 0. Now we know our zero product property tells us we can set each factor equal to 0. So 2x minus 1 equals 0. X plus 2 equals 0. We solve each of these now. That's 2x equals positive 1. Divide by 2, x equals 1/2. And over here, we're just going to subtract the 2, so we get x equals negative 2. That means that our vertical asymptotes are going to be x equals 1/2 and x equals negative 2. Notice here they are actual vertical lines, right? So we need the x equals part of our equation. Okay, so when you write out your vertical asymptotes, make sure it's x equals whatever value and x equals whatever value. Now, in terms of horizontal asymptotes this time, first thing we have to look at are the exponents in the numerator and denominator. Now, notice this time we have a degree of 2 in the numerator, we have a degree of 2 in the denominator. We said if those exponents are equal to each other, then we're going to divide the leading coefficients. That means that my horizontal asymptote this time is going to be at y equals 3 over 2. So again, just to recap, always factor first if possible. See if you have any factors that cancel out. Then we're going to set the denominator equal to 0 to find our vertical asymptotes. Then we're going to use those 3 rules to decide where the horizontal asymptote is going to be. In this case, because the degrees are the same in the numerator and denominator, we're going to divide those leading coefficients. That's how we get y equals 3/2. All right, so this time it asks us a graph. What we're actually going to do is the same thing we did on the last one. Look for those horizontal and vertical asymptotes, and then we'll talk about domain and range. So again, I want to see if I can factor this first. So if we look at our numerator here, factors of 2x squared would be 2x and x. Factors of 4, I could either use 2 and 2 or 4 and 1. I know I'm trying to get a 7 in the middle, so I'm going to go with 4 and 1. That would give me 8 and 1. We'll do a positive 4 here and a negative 1 there. That would give us 8x minus 1x. That would be 7x in the middle. Over. Same thing with the denominator. Let's see if that factors. X squared has to be x and x. 2 has to be 2 and 1. And then we look for the signs here. We're going to need a positive 2 and a negative 1 to give us that positive x in the middle. Then we look to see if any factors cancel out. In this case, we don't have any common factors in numerator denominator. So now we can just set our denominator equal to 0. So we're going to have x plus 2 times x minus 1 equals 0. Set each one of those equal to 0 now. And that's going to give us x equals negative 2 and x equals positive 1. These are the vertical asymptotes this time. Now, in terms of horizontal asymptotes, again, I'm going to look at my rules. I notice again that I have an x squared here, an x squared here. Therefore, I can use that same rule that we did on the last one. Divide the leading coefficients here. So that's going to be 2 over 1. So we're just going to get y equals 2 as our horizontal asymptote. Now, once we have the asymptotes, the domain and range should be pretty basic, right? So we're just going to say, well, we know the vertical asymptotes are going to be restrictions on the domain. So when I list out my domain this time, it's going to go from negative infinity to negative 2, union. We need everything between negative 2 and 1 now. And then we want to pick up with 1 and go all the way to infinity. Okay, so those vertical asymptotes are the only restrictions on the x values. Okay, so when we list out our domain now, we just need to make sure we put those restrictions in the domain. Now, same thing with horizontal asymptote. That's going to be the only restriction on the range. So in terms of range this time, we're just going to go from negative infinity to 2 and from 2 to positive infinity. Now, it's always a good idea to check your graph, okay? Because again, it is possible that your graph actually passes through a horizontal asymptote somewhere in the middle. And if that happens, then we can go back and adjust what that range actually is, okay? So let's take a look at the graph in Desmos. And we'll see if this actually checks out for us. Okay, so this time we had 2x squared, 7x minus 4 over x squared plus x minus 2. Right, so what I'm going to do is I'm going to put the asymptotes that we found on here. So we said there should be one at x equals negative 2, should be one at x equals positive 1, and then we said the horizontal asymptote was at y equals 2. So I'm just going to look at one at a time just because that's a lot to put on the graph at once. So now if we look at this first asymptote, notice here that does check out, right? So we notice here that our graph does approach that vertical line. So that is one of our vertical asymptotes. It's never going to pass through that. So that is a restriction on our domain. So we do have a restriction at negative 2. Now, if we look at the asymptote at x equals 1, same thing. Our graph is approaching that, never going to cross it. And so we can say that's definitely a restriction on the domain. So our domain looks good. Now let's talk about the range. So remember we said there was a horizontal asymptote at y equals 2. Well, that only means that as I go to positive and negative infinity, my graph is going to be approaching that value. Okay? And we can see that that's actually happening here. But also notice that the middle part of this graph actually passes through that value. So I actually have a y-intercept here that goes through 2. That's a point on my graph. That means that there's actually no restrictions on the y value this time. So we need to go back and adjust our range. So just because there's a horizontal asymptote does not necessarily mean that the range does not include that value. Okay, so always keep that in mind. Take a look at your graph, right, because that can actually help you out to see the range. So when I go back to the notes now, for our range here, instead of saying from negative infinity to 2 and 2 to infinity, we're still going to say that the range is just negative infinity to positive infinity, because it does actually cross through all those y values. And again, keep in mind you have access to Desmos for your test. You can use a graphing calculator if you'd like to. Okay, so always use your graph to your advantage when you're looking for domain and range. All right, so now I want to graph the following functions. So again, first step, we're going to factor, see if we have any common factors, and then we'll go from there. If I look at the numerator of this one, x minus 3, that's already factored, nothing I can do with that. I have a common factor of x down here, though, so I can factor that out, and that would leave me with x minus 3. Now notice when I do that, I actually do end up with a common factor of x minus 3 in the numerator and denominator this time. So this is actually just going to simplify to 1 over x. That means when I'm looking for vertical asymptotes this time, I'm only going to look at that final answer, okay, once everything is canceled out, and I'm going to use that. Well, the only thing left in the denominator this time is an x. So that means that x equals 0 is a vertical asymptote. Now, for horizontal asymptotes, remember we look at the degrees in the numerator and denominator. Well, in this case, we have an x to the first power in the numerator, we have an x squared in the denominator, and our rule said that if the numerator's degree is smaller than the degree in the denominator, this is automatically going to be y equals 0. Now, the graph of this one is going to look very similar to that very first rational function we looked at because it simplifies down to 1 over x, right? So we know what that basically is going to look like. However, in this case, there is still that factor of x minus 3 before we canceled it out. We have to consider that that's still a restriction on the domain here. And so we still know that x minus 3 cannot be equal to 0, which means that x cannot be equal to 3. So when you're talking about the domain this time, it's going to go from negative infinity to 0, from 0 to 3, and from 3 to positive infinity. And again, this is the domain because we have to go back before we cancel anything out and consider any restrictions on that original function. Therefore, 3 is actually a restriction on the original function because that would make the denominator equal to 0. Notice, though, it's not a vertical asymptote. Okay, so let's take a look at this graph, see what it actually looks like, and see what's actually happening at 3 this time. Let's switch back over to Desmos. And so I'm going to graph y equals x minus 3 over x squared minus 3x, right? That was the original function. Again, notice here, it looks very similar to that first graph that we looked at, just the basic 1 over x, because that's what it simplifies to. We do have the horizontal asymptote at y equals 0, that checks out. We do have the vertical asymptote at x equals 0, that checks out. Now the question is, what's happening at 3? Okay, so what I'm going to do is I'm just going to trace my graph over here. I'm going to trace until I get to 3. Let's see if I can get right on 3 here. There it is. Notice that when I pass over 3, it says 3 is undefined. So what happens is there's actually a hole in the graph at that point. Okay, so we have to remember in this case that it is not part of the domain, right? 3 would make the denominator 0, that would be undefined. So there is going to be a hole in your graph, but the rest of the graph is going to look like your basic 1 over x graph. Okay, so now what we would say is there's a hole at x equals 3. Okay, so if you were trying to graph this by hand, you would actually put just an open circle at that point, right? You would graph 1 over x, you'd put your asymptotes at x equals 0, y equals 0, and then you just put an open circle there at x equals 3 on that graph. Again, that's extremely important in determining your domain. Always go back to the original function and find all the restrictions on the original function, not just what you get once you've simplified and canceled out factors. All right, let's take a look at this second one. So same thing, I'm going to factor first. Notice here we've got an x squared, common factor, and leave us with x minus 2. I have an x minus 2 in the denominator. Those are going to cancel. So this is actually going to give us x squared. Now this time, x squared is just the graph of a parabola, right? So that's what this graph should look like. But we have to keep in mind here that we do have a restriction on the original function because it had a denominator. So we still know that x minus 2 cannot be equal to 0, which means that x can't be equal to 2. Now, that's not going to be an asymptote this time because it's not present in the final answer, right? It's not part of that final function that we get. So that means there's going to be a hole at x equals 2. So in terms of our domain this time, we're going to go from negative infinity to 2 and 2 to infinity. In terms of vertical asymptotes, though, there are none. And in terms of horizontal asymptotes, remember we said if the degree of the numerator is bigger than the degree of the denominator, then there's not going to be a horizontal asymptote either. So again, if we were to graph this now, it would be a parabola. We'd have a hole at x equals 2. That would be the only thing that's missing from our domain, and there will be no vertical or horizontal asymptotes because it is going to just be a parabola. All right, so let's see if we can graph this one now, or just think about what all the parts are, and then we can look at it in Desmos to check everything. So again, first step, I'm going to see if this thing factors. So do x and x. Factors of 5 here would be 5 and 1. I need a positive and a negative. The 5 needs to be the negative. The 1 needs to be the positive. We're going to put that over x minus 3. No common factors this time, right? So nothing's going to cancel out. So now let's look for vertical asymptotes. I can take my denominator, only one factor this time, set it equal to 0. So that's going to give us x equals 3 as our vertical asymptote. Right? And that's the only vertical. Now, horizontal asymptotes this time, we look at our degree. We have a 2 up here in the numerator. We have a 1 down here in the denominator. That's bigger in the numerator than it is in the denominator. So remember we said that means that there are no horizontal asymptotes. Now notice this time up in the directions, right, it says that we could have what's called a slant asymptote. If the degree of your numerator is exactly 1 more than the degree of your denominator, then we have to check for slant asymptotes. So since we have a 2 as our exponent in the numerator, a 1 as our exponent in the denominator, we're going to try to find a slant. The way we're going to do that is we're going to use long division now. I'm going to put x minus 3 on my outside. That's what I'm dividing by. X squared minus 4x minus 5 on the inside. So we have to remember back to long division. Remember, we ask ourselves first, how many times does x go into x squared? So I'm dividing x squared by x, just the first term and the first term. That's going to give us x. I put my x up top. Now we distribute. X times x gives us x squared. X times negative 3 is negative 3x. Group all that together and subtract. X squared minus x squared cancels out. Negative 4x minus a negative 3x, that becomes addition. So this is just going to give us a negative 1x. Bring down the minus 5. Now we ask ourselves, how many times does x go into negative x? So negative x over x is negative 1. We get a minus 1. We distribute. Negative x plus 3. Group that together and subtract. Negative x minus a negative x, that's going to cancel because that becomes addition. Negative 5 minus 3 gives us negative 8. That's our remainder because x does not go into negative 8. In terms of our slant asymptote, though, okay, so we're looking for a slant asymptote. All we care about is this quotient up here. We can completely ignore the remainder. And so our slant asymptote for this one is going to be y equals x minus 1. So we have a vertical asymptote at x equals 3, no horizontal asymptote because our degree in the numerator was bigger than the degree of the denominator. And then we have a slant asymptote now at y equals x minus 1. Again, we found that by using that long division. Now, I do want to look at this one in Desmos so that we can see what that actually looks like. So our original function here, we had y equals x squared minus 4x minus 5 over x minus 3. So first, I'm going to graph that vertical asymptote. We said that should be at x equals 3. And you can see that here. If you want to zoom out a little bit just to kind of see how it's approaching that vertical line, but that does check out. Now, notice here there is no horizontal asymptote because as I go to infinity and negative infinity, my y values are also going to positive and negative infinity. So what I want to look at now is that slant asymptote that we found, y equals x minus 1. And notice that green line now, the left-hand side of the graph is approaching that line from above. The right-hand side of my graph is approaching that line from below. So that's what we call a slant asymptote now. And so that's how we get that. That only happens, though, if the degree in the numerator is exactly 1 more than the degree in the denominator. Then we can do our long division and find that slant asymptote. All right, so that's all we've got for that section. As always, send me questions as you have them in WebAssign. Come see me during student hours if you need to. Have a great day, and I will see you next time.